All right, so now that we've looked at the silicate tetrahedron, SiO4, let's now extend that out to larger silicate structures and see if we can kind of predict based on the stoichiometry. All right, and we do that by, again, those bridged versus non-bridged oxygens translate into different oxygen to silicon ratios. And so that allows us to predict the structure based on that ratio and based on the ratio of non-bridging oxygens. And so the table that we're going to take a look at is table 3.4 in your text. And this gives that relationship between the oxygen to silicon ratio, as you can see in this column, versus the type of structure that you'll see here, and then the N words over here. And it also gives you the number of bridged versus non-bridged. So again, the more bridged means the more connected or networked the structure is. And then the higher the oxygen to silicon ratio, the more non-bridging and the more isolated the tetrahedron becomes. So the first one we're going to look at is the lowest oxygen to silicon ratio. And you have the lowest amount of oxygen to silicon, too, when everything is bridged, because we have less and less oxygen. And so this is an example of silicon to oxygen ratio of 2. And if you think about what that implies, 2 oxygens for every silicon, that's SiO2, right? So you probably heard of this. This is silicon dioxide. It's also known as silica, which is basically quartz. Cristobalite and tridymite are all kind of polymorphs of that structure. And if it's amorphous, that would be the basics of fused quartz as well. So these are all networked structures. So we take the basic tetrahedron in this shape and network everything together so that all the oxygens are bonded to another. So you see that in the quartz shapes down here, and also the tridymite and cristobalites that you see, they're all bridged. They're all networked, and so you form a 3-dimensional structure, a network, like one of these. So there's a number of different structures, but these are 3 of them. So that's what you get when the oxygen to silicon ratio is the lowest. You get a 3-dimensional network structure. If we have more and more oxygen relative to silicon, that implies that the number of bridged oxygens goes down and the number of non-bridged goes up. So if we have the next highest number is 2.5, this implies we have a sheet-like structure that you see here, so like a planar structure. So they call it infinite sheets. So this could be clays form into this structure, and others as well, which I have on the next slide. And then just to go on to the next ones that we'll talk about as well, if we keep going up, we go into less and less dimensionality, right? So 3-dimensional network was 2, planes, which are 2-dimensional structures, are 2.5, and then we have chains, which are more 1-dimensional structures as we get closer to 3. All right, so let's look at some examples of these sheet structures. So you're probably familiar with some of these, mica, talc. If you see these in their mineral form, they often look flaky because those are the individual planes coming across, separating. So that's what you can see with mica, and you can see that as well. It's the same thing with kaolinite, which is basically a clay-like material, has this layered structure as well. And so these are the actual structures that you're seeing. And so in essence, we have some type of layered structure. This one has potassium in the middle, and then we also have this sort of hydroxyl group in the middle of this one as well. And the same thing we can have on these other structures. And here we actually can have water form in between the layers, but they all have a layered structure with planes in between. All right, so in these clays, the kaolinite is an example of one. Aluminum kind of plays this interesting role. So aluminum is part of this structure. So it's not just SiO2 anymore, or SiO. It's not just that. There's actually some aluminum. And aluminum is kind of interesting because it can substitute in multiple ways. So in this case, the aluminum 3 plus can occupy either the octahedral or tetrahedral holes in the network. So you kind of see it acts as a loose ion, a free ion in this structure. So it's not connected to the Si2O5 layer, right, which is the sheet. It's in between. And so it can occupy itself in those areas. However, if we have something like mica here, we see that we have aluminum in these same positions and in between the layers, not attached to the networks, but we can also have it as part of the network. So it can actually replace the Si4 plus within the network in those cases. And so when you see something like this, you see the Si3O10, but we also have aluminum, and the aluminum being here implies that it's part of this network. So here with these triangular tetrahedron shape, that has aluminum in it. So it can either be part of the network or it can be a free ion. And so these are kind of interesting structures because it can be either one. Additionally, there's an added effect because aluminum, the ion 3 plus, has different charge than silicon. So if it goes into the network, there's a difference in charge here, right? There's a +1 difference, a -1 difference. And so there has to be some additional charge compensation. And so the way it does that is we tag along some other extra cations. So for example, potassium has a +1 charge. So +1 +3, it compensates the charge of the silicon. So anytime aluminum forms into the network, it also has to have something else to balance the charge, and that means it has one of these free ions that's not part of the network. And so that creates an additional alkali earth metal along with aluminum. So aluminum is kind of this interesting role in glass because of these factors. So the aluminum in the network's here, but it also has to compensate with the additional potassium. All right, so in terms of glass, because glasses are just amorphous versions of all of these silicates, we see that the same thing holds true. So this table is from another text, but it just shows that the cations can be divided in different ways in which they interact with the network. So the silicate network, and then if it's amorphous, the glass network. So obviously silicon is what we call a glass former because it's part of that network, the SiO4 network. But aluminum can also be a former because it forms into the network. But you also see here it's listed as an intermediate because it forms into the network and is a former, but it also carries along with it those modifiers, those free ions. And so potassium is one of those, sodium can be another, calcium can be another. And so those are the ones that disrupt the network, like the potassium you saw here in this structure. It kind of disrupts the network around it because it's one of those alkali earth metal ions. So this is just kind of a detour mentioning glasses because we'll talk about glasses here in the near future, but also it connects back to the silicate structures very much. All right, so we talked about the three-dimensional structures, we've talked about the planar structures, and the last kind of one here I want to talk about in this module is these more linear structures, which are chains. And there's actually two types. There's what we call a double chain, which has an oxygen to silicon ratio of 2.75. And then we have a single chain, or just a chain, where the ratio is 3. So a double chain is kind of like you see here. So it's still linear, but it is composed of two layers of tetrahedral forming that chain. So the famous example of that is asbestos. So you see asbestos here, it forms into those fiber-like forms, and that's because it is this chain shaped, right? So chain is very linear, and a fiber is obviously very linear as well. And so it forms into that because of the structure of the silicate, and that's what gives it its properties, right? It forms into fibers, and therefore it's a natural insulator because it has a lot of air around it, which is a very good insulator. And so it's used in insulating materials, or used to be, because we all know now that now these fiber-like structures are very fine, and they can actually break off into small pieces and get basically attached to your lungs and cause cancer. So it's kind of a double-edged sword for the structure here. The structure causes the fibers, which is good, but the fibers also have negative effects as well. And then the other chains as well, there's examples down here, but they would have an oxygen ratio, and we're getting more and more non-bridged oxygen. So there's less of those bridged in these cases.